Hello, everyone. Come on in. Looks like everybody's in here now. Hey, everybody. I did actually have the Zoom meeting open. It was just I was testing, making sure everything was working. That's why I didn't let you in yet. I usually will let you in, but if I'm so early, a lot of times I'm just testing to make sure stuff's working. Of course, that doesn't mean it's going to continue to work, but anyways, that was the goal. But you're in now. Does anyone have any questions about anything? Hopefully, I think you remembered and or saw that I pushed the test date back. The homework, depending on how things go today, well, for you guys, you're Tuesday, Thursday, so it won't be a problem. Yeah, so our homework for chapter 23 will be due September 11th, but this is a chapter where it has two parts of homework. So it's a part one and then a part two, in addition to the conceptual. So what I'll do is the part one will be due by the 11th, but I give you to the 13th to do part two. So that shouldn't be a problem to you guys. If I find it is, I'll let you know. I'll first change the date and then let you guys know. But y'all should be able to get all that done by a week from a week from tomorrow for the second set and by Monday for the first set. So does anyone have any questions? Can anyone not hear me? Okay, looks like everybody's hearing me then. Of course, it's not really very good logic that gave me that response, but anyways, I'm sure you would chat me something if in fact you didn't hear. Let's say Christian, can you hear me? Can you send me a chat or speak if your microphone's working? I've got nothing.
Yeah, I'm able to hear you.
I assume that's always the case, but I have actually had several instances where I've been talking for 10, 15 minutes and the audio just not be working. So what we're doing today is I think I hinted to chapter 23, but I haven't done much with it. But chapter 23 is basically on electric potential. So just like when you were in 241, you first studied mechanics, but mechanics is broken up into kinematics and then dynamics. And the kinematics included basically how motion causes things to move, if it's an acceleration or velocity or whatever. How does that move over time and over space without any understanding or care of what actually caused that acceleration or that velocity and how it was caused. Then we got to the dynamics part, and that was F equals ma basically, but included Newton's first law of motion, Newton's second law of motion, Newton's third law of motion, all of which more or less hinged on vectors. So we then started a series of different types of problems using vector calculus in some sense, but mostly just plain vector algebra. Well, after that, we found that we could do a lot of the same stuff, but different variables were more important than the previous ones. And certain variables that were important and easy to get in the previous ones were actually not that important to get in the new ones. And that was a conservation of energy method, and we didn't use vectors. So we're going to do sort of the same thing now. We're going to switch from using a mostly vector analysis to one of scalars. And I've mentioned it before, I'll mention it again, but basically whenever you have what's called a conservative force, there's a cascade of events that makes, or a cascade of facts that makes true. First, if a force is conservative, then all these things I'm getting ready to say are also automatically true. And what that means is even if one of them is true, then all the other ones have to be true. So the force field is conservative means that if you take that vector gradient operator that I have hinted to you at, which is basically a vector operator that has as its x component a partial derivative with respect to x with an I hat in front of it, and its y component is j hat partial with respect to y, and its z component is k hat partial with respect to z. if you put that in the second row of a matrix with I, J, and K as a top row, and then you put the vector field in the bottom row, take the determinant of that, then you have something called the curl of the field. And that curl is called del cross F or del cross E, depending on which one you're wanting to deal with, the force field or electric field. But the main thing is if that is identically zero, meaning not zero for a special X, Y, and Z, but zero for all X, Y, and Z, then that's called a conservative force. That's the definition of conservative force. And if it's a conservative force, also you have the curl is equal to zero. Also, you have that there exists a scalar potential, say U or V, such that the line integral of, or excuse me, not the line integral, but the U final minus B final, meaning the U at the end point minus the U at the beginning point, which is changing U, is equal to F of something. In other words, it doesn't depend on the path whatsoever, which is the same thing as saying that the integral work F dot dx from A to B depends only on A and only on B. It's also equivalent to saying that if you do work in a complete circuit, so you start at some point in space here and you go all the way around like this and end up at the exact same spot, then the net work done is automatically zero. And that scalar potential turns out to be, you can actually get that electric field or that force field by taking the negative gradient of that U function that you found. All of those are equivalent. And like I said, if any one of those principles are true, then they're all considered true. So that's sort of the theory behind all this stuff. And it was true for gravity. That's why we were able to introduce potential energy, both in close to the Earth's surface was mgh, but when we weren't close to the Earth's surface, it was negative gm over r. And that was the gravitational potential energy. Well, similarly, we're going to introduce a scalar potential. And that scalar potential, we're just going to call U. But we're going to define another quantity because we did do force. Remember, I said if a force field is conservative, that potential energy still exists as a force field, but there's going to be a quantity that, just like us going from the force field to the electric field, we ended up dividing out the Q that was being affected by it. Well, you can do the same thing with potential energy and get a potential energy per unit charge, and that's called the electric potential or the voltage. Are well, basically that's another type of scalar potential, let's put it that way. So, and it is the same voltage that you've heard of when you talk about the electricity coming into your house and all that good stuff. So that's what we're learning about now. So let me go ahead and attempt to share my screen with you. As I said, that was working earlier, so hopefully it continues to work now. What I'm going to do is say share screen right here. Oh, great. Now it's acting like I need to download something again. That's so helpful. Why does it do this every time? And now, I don't know why it didn't ask me that earlier, but now I'm supposed to share screen. Let's see if it's going to work. Please do, please do, please do. Yes. Oh my gosh, I can't believe it. So it's amazing. Okay. So now I'm sharing my screen with you, which has really nothing on it. But the main thing I'm trying to show you here is that before we had potential energy U, and you have a quantity called delta U, which is the change in potential energy, which might be equal to UB minus UA, where A was your initial position and B was your final position. So you're doing final potential energy minus initial potential energy. Well, as we learned back then, that was equal to the negative of the work done, which is the integral of F dot dl, which is in fact a line integral. Again, as your textbook mentioned earlier, when we did this in chapters 7 and 8, this is technically a line integral, and basically what it means is you're taking a dot product of the force vector with the vector sort of like a tangent vector to the path that you're on, and you're taking it at each individual point, because f can in principle be a function of x, y, and z. So at different x, y's, and z's, you're going to have a different f, which could mean a different angle, a different magnitude, or both. And then dl, of course, is going to have a different direction as well for each x, y, and z. And you integrate that from a to b. This part right here is the negative of the work done from A to B, okay? Well, what we're going to introduce is, notice this U, which has units of joules. We're going to introduce a new quantity, V, such that delta V, which is VB minus VA, is equal to negative integral of, let's write it this way. Okay, this charge down here, Q, is the charge that is being moved. Okay, so this ends up becoming negative integral of E dot dl. And you can notice the units of this is the joule per coulomb, where coulomb's unit of charge. And in fact, this is called voltage, electric potential, or electric potential difference. Those are all words for the same thing. Notice what they do not have in them is the word energy, which is what this was. And in fact, 1 joule per coulomb is defined to be 1 volt. So notice that's a capital V for that unit, and that's named after Alejandro Volta. Okay, any questions on that? All right, so that's the idea of what this voltage is. Now, if you think, for instance, about a plate of, say, positive charge and a plate of, say, negative charge, okay, and that actually will establish an electric field that is essentially uniform from here to here, equal to E, which we know is, of course, sigma over epsilon naught, where sigma is the charge per unit length. Okay, but we're just, the main thing we're saying is that the electric field is essentially uniform, at least towards the center of these, as we've seen in the actual graphing electrical potential lines. We see that it starts to flare out a little bit near the edges. So the electric field points like a little bit out, but in the center it's that way. So let's imagine a positive charge right here being moved to right here. So this is position A, and this is position B, and this distance right here is, say, D. Okay. Well, we could define our coordinate system such the x-axis is right here, and the origin, of course, would be at the plate. What we'd say then is the change in potential energy, delta U, which would be UB minus UA, would be equal to the negative integral from A to B of F dot DL. Well, in this case, the F is just Q times the electric field, where we're going to say this is the charge Q. So we get negative integral of Q E. And that E, of course, points in the I hat direction. And we're moving it. Now, here's the trick with line integrals. This dot DL, you either have to use the direction of the DL or the order of the end points to define which direction you're going, but not both. Okay. In one case, you're supposed to leave it in the positive coordinate direction. And the other one, you're supposed to choose the direction that it's going. So if you want, for instance, in this case, to choose the direction we're going to dictate what which direction we go, then you would write DL I hat, and then the A to B would indicate just a positive coordinate direction. In this case, both are positive, so it makes no difference whatsoever if you did both of them. But it does matter when you start to play with negatives. So in this case, I'm going to say DL is DX I hat, and I'm going to pretend like that's actually choosing my coordinate direction. And then the positive coordinate direction is from X equals A to X equals B, because A is smaller than B, because A is at the origin. Okay. Well, you can see that I hat dot I hat is 1 times cosine of 0, which is 1 again. So that just disappears. And that was supposed to be a DX that I put there, but all I put was the D and then the I hat. Let me fix that. Whoa, still got my eraser there. So in this case, this gives me QEX with a negative in front of it times X equals A to X equals B. So this is negative QE. And now in this case, we're going to write A, which is X equals 0, or excuse me. We're going to write X evaluated X equals B, which is D, because actually it's a distance of D to the right, minus A, which is a distance 0 from the origin. Again, I'm assuming that's a point particle. So I get D minus 0. So I get negative QED. So this suggests that the potential energy went down, and that should make sense, right? The negative charges are attracted to the positive charge, or more importantly, the positive charge is attracted to the negative charge. Okay, so the fact that that and the positive charges are repelled by the positive charge wall tells you that it was very uncomfortable when it was at A, but it was more comfortable at B. So this should have been a decrease in potential energy, and that's exactly what the negative sign told us. This would come out in units of joules. Now, the change in potential, delta V, would be VB minus VA, which is the negative integral of just E dot DL, okay? And that's from A to B. So if I implemented this, I get negative integral E, which is a constant, like we said before, sigma over epsilon naught, and it's pointing in the I hat direction, dotted with, this time I'm going to use my coordinate direction to indicate the direction I'm going. So I'm just going to blindly call DL DX, which is in the positive coordinate direction, times DI hat. Okay, the DX I hat's automatically the positive coordinate direction. I'm going to let my range of integration dictate which direction I'm going. So I'm going from X equals 0, which is the same thing as A, to X equals D, which is the same thing as X equals B. Okay. So again, we get a negative because the I hat, or because the dot product is a what we call a linear operator, you can pull the dx through the dot product to the other side of the other I, and it'd be e dx I hat dot I hat, but I hat dot I hat, like I said before, was 1. So I just get the integral from 0 to d of e dx, which equals negative e d times d, or excuse me, negative ex evaluated from x equals 0 to d. So ultimately my delta v is going to become negative e times d, and this has units of volts. Okay. So this is an actual real expression. The change in voltage is E times D, but that only works with a constant electric field. And that's what I happened to be working with when I did the this capacitor, because the capacitor, usually the plates are so large compared to the separation between them that the electric field is essentially uniform all the way throughout and has no dependence on Z or any other variable. Obviously, you can look right here at this graph of the electric field on the between the parallel plates, and you see as you get near the bottom or the top, this does in fact have some dependence on position, but we just have to stay away from that particular area, or this particular area, or excuse me, the top particular area. So that is an actual equation. V in magnitude is equal to E times D. And actually, I'll go ahead and, well, I'll just leave it like that. But just remember, this is for constant uniform E. Okay, that's the only case it works in. So it's not the norm by any stretch of the imagination. Anybody have any questions on that? Okay, so what we got was that the change in potential energy was negative QED, and what we got was the change in electric potential was negative ED. So let's write that down. Delta U equals negative QED, and delta V was negative QE. Now, another thing you can say about that is basically that you can always find the change in energy, delta U, is equal to Q times delta V. So that's a general expression that is true. If you find the electric, the change in electric
V ED.
Yes, yes, but that's only for, again, the uniform electric field. Or did you ask me what was
negative QE? Isn't that force?
Oh, excuse me. Thank you. You did that right. Yeah, I see what you're saying now. Hold on a second. Yeah, delta V. That's what I said. Sorry. Yeah, I started. The whole thing was bad from the get-go. So the delta U equals Q. Negative QED is right. Where I screwed up was when writing this. I'm glad you caught me on that. That would have been a real pain in the butt. So delta V turned out to just be ED. Now from that, you can see that. Sorry about that, and thanks again for catching me. Now you can see that delta U is just Q times delta V. Okay, so this is generally true. And this is only true. And I'm going to do it like this and come over here and say this way too. Only true for E equals a constant electric field. Okay, so that formula gives us something that actually helps us as with a new equation, but it also introduces us to another unit. So in fact, we normally work with this side being joules, and then this little part right here being volts. I don't know why I wrote a 1 there. I meant to write a J there. Okay, this side being joules, and this part of the right-hand side, the delta V part, just being volts. So that tells us something, but it introduces us to another unit that's more helpful when dealing with particles like electrons and protons and stuff like that. So for particles, joules are not convenient. So we use electron volts. Well, I can do better than that. And that's given the symbol lowercase e, uppercase V, like that. Where 1 EV is defined as the energy received by an electron and going from negative 1.000 volts to 0.000 volts. So 1 electron volt is equal to, using that same equation, we'd say it's equal to E times delta V, which equals negative 1.602 times 10 to the negative 19th, because that's the actual charge, coulombs, times 0 minus 0.0, excuse me, minus minus 1.000 volts, which gives me positive 1.602 times 10 to the negative 19th joules. That turned out terribly. Let me say right over here. Gives me positive 1.602 times 10 to the negative 19th joules. Okay, so that's a new unit that we can use, and that comes in kind of handy. Obviously, when we start talking about electrons, protons, neutrons, that kind of thing. The other thing that we need to consider is conceptually, what happens if we do that same experiment that we did earlier, where we were thinking about this positive charge being moved from the positive plate to the negative plate? What happens, for instance, with that if we do it with a negative charge, moving it from a positive plate to a negative plate? Okay, so let's look at that now. And I just used my eraser to erase the under parts of all my letters. Looks like the only one that was damaged was the joule and the 0 and the 1. All right, so let's imagine again a plate, positive charges, and then another plate with negative charges like this. And let's say right at the origin again, we have a negative charge, negative Q here. Okay. Now you can see, because it's positively charged, you can see that this is high voltage. And this over here, because of negative charges, is low voltage. In other words, what that means is positive charges would run from that positive that positive charge towards the negative charge. Now we're going to move it from here A to here B. And we're going to see what happens to the electric potential. So again, in this case, delta U, which is UB minus UA, is equal to negative integral of F dot DL. In this case, the F, which again, we have the electric field pointing this way. That's another reason to know that the high voltage is the left-hand side, because the electric field runs from high voltage. So we're going to say this is, in fact, the force on this charge is negative Q times the electric field dotted with DL, which I want to see those two negatives canceling out already. And I want to say E, which points in the, and I'll pull a Q out in front too. E is just E times dx I hat dotted with, this time I'm again going to use my direction. I'm going to use my DL vector to indicate my direction. So I'll make that dx I hat, because it's actually moving in the positive X direction. Because again, my coordinate system is the x-axis going that way. And I'm going to use my range of integration. I'm not going to use it at all. I'm just going to put from low number to high number. So that's from 0 to D again. Okay. And I do not know why there's a dx in there. Let me fix that real quick. I think I got ahead of myself a little bit when I was writing the E. So this is going to be E I hat dotted with dx I hat. And we use this dx I hat to indicate direction. That meant we just had to go from low coordinate to high coordinate for the range of integration. So in this case, I'm going to get Q times E times D minus 0, which is positive QED. So that meant the potential energy actually went up. And that makes sense, right? Because just like before, we've got like charges next to each other. But in the first case, it was positive charges being up against a positive wall. Now I got a negative charge being up against a negative wall. So delta U is greater than 0. So this is not what an electron would do on its own. It would, in fact, go from B to A. Okay. Now, on the other hand, delta V, which is VB minus VA, is in fact negative integral E dot DL, which is negative integral. I'm going to use the range of integration this time to decide which direction. So I'm going to say it's going to go from 0 to D. And the E is pointing in the X direction. So that's E I hat dotted with the positive coordinate direction is just I hat direction. So I write DX I hat. And let's kill a little bit of something here. Which I think you can see is clearly going to give you negative E times D. Okay. So electrons actually move in the direction of decreasing in the direction of decreasing potential energy, like protons do. Everything moves in the direction of decreasing potential energy, but not everything moves in the direction of decreasing electric potential. So not everything moves in direction of V decreasing. In fact, only positive charges do. Okay, so that's a key point to understand here. If you start to get lost in your signs and stuff like that, because a lot of time we just use these equations and we drop the signs on the charges, all sorts of stuff like that. If you ever get lost about what sign something should have, just remember positive charges and negative charges all move towards decreasing potential energy. Okay, you got to have the word energy on there. However, only positive charges move to decreasing electric potential. Negative charges move to increasing electric potential. Notice I didn't say energy on those last two. Any questions on that? All right, so now that we have these few things that we've written down, we can do stuff like compute the kinetic energy that an electron might have upon going through 5,000 volts. So let me do a problem like that. An electron moves spontaneously. That means on its own without someone having to push it along, spontaneously across an electric potential of 5,000 volts. I'll put a dot there so we'll know that that's 4 sig figs. What will be its final kinetic energy if it started at rest? I want this answer in joules and in electron volts. B, so that's going to be part A. How fast will it be going? Sorry, I switched switched the cursor for some reason. How fast will it be traveling? And C is delta U greater than or less than 0. And then part D is delta V greater than or less than 0. Okay, so there's a pretty big problem. We have an electric field, an electron moving spontaneously, meaning that because of the electric field and voltage and all that stuff that's established, the electron just starts moving on its own from rest and moves across an electric potential difference of 5,000 volts. I didn't tell you whether that was positive or negative. And I want to say, I want you to figure out what will be its final kinetic energy if it started at rest. And then B, I want you to find out, oh, by the way, in that, I want you to calculate both joules and electron volts. And B, how fast will it be traveling? And C, is delta U greater than or less than 0? And D, is delta V greater than or less than 0? So let's start with part A first. What we do know is that delta U is equal to Q delta V, right? So if we think nothing about magnitudes, we can say, well, initially we had U initial, but then afterwards we just have K kinetic energy final. So we can say, in fact, that delta U would be equal to KE final, at least in magnitude. And we're going to say that's equal to 1.602 times 10 to the negative 19th coulombs times 5,000 volts. So I'll just make a note here, ignoring signs. Okay, when we do that math, 1.602 times 10 to the negative 19th times 5,000, and I get 8.01 times 10 to the negative 16th joules, and actually that's 8.01 0 because it's 4 sig figs in both, and that's my kinetic energy as well as my potential energy final, because we started from rest, right? So I'm going to box this off. Now, what is the kinetic energy final? Whoa. What's the kinetic energy final in electron volts? I can convert it, but I want to show you how silly it is to convert it in a second. So I'm going to say 8.010 times 10 to the negative 16th joules times, I know that 1.602 times 10 to the negative 19th joules is equal to 1 electron volt. So I'm going to get 5.000 times 10 to the third electron volts. But that's the beauty of the electron volt, is you don't have to use the electron charge anymore. You just say the number or the kinetic energy in electron volts is just 5,000 electron volts. If it was 100 volts, you'd say it's 100 electron volts. So you don't really technically have to do that conversion, but the main thing is that you understand it well enough that you either use the conversion because you know how to use it, or two, you just understand it enough where you can just take the voltage and stick it in front of the other unit and you're good to go. So that was part A. Anybody have any questions on that? So part B is how fast will it be traveling? So that's not a part of the problem that lends itself easily to electron volts. So I'm going to go back and use the 1/2. We're going to assume it's not relativistic. 1/2 mv squared is equal to 8.010 times 10 to the negative 16th joules. And I'm going to say that V final is equal to 2 times 8.010 times 10 to the negative 16th joules over. Now the mass of the electron is 9.109 times 10 to the negative 31 kilograms. Now, I wouldn't expect you to know that. I mean, if you're a physics major, you should know that by now. But yeah, I mean, well, I shouldn't say by now, but really soon you should. But that is something in this class that if I didn't give you, you can just ask me for it and I will do it, but I should have given it to you. So everybody see that I just basically multiplied kinetic energy by 2 and divided by m and then took the square root. So V final is going to be equal to 2 times 8.010 times the negative 16 divided by 9.109 e to negative 31. That gives me the square root of 1.7587 times 10 to the 15th meters squared per second squared. Notice that's how the units actually work out. I got to take the square root of that. And I get dangerously close to, actually, I did this problem for you already. I remember now. Dangerously close to the speed of light. So this was probably a case where I should have used relativity, but I didn't. Okay. Now, finally, or actually, I shouldn't say finally. Does anybody know what the definition or the answer to C is? Did the potential energy for this electron moving spontaneously, did it go down or go up?
Went down.
It went down. So delta U is less than 0. Because that's what things do when they move spontaneously. How about the electric potential? We know that they're related by that equation that I wrote next to the letter A, only that includes the sign. So I think that's one way you can just do it brute force and tell you whether delta U is less than or delta V is less than or equal to 0. But you could also figure it out from the context that I gave you earlier, that electrons don't move to decreasing electric potential. They actually move to increasing electric potential. So delta U or delta V is in fact greater than 0. Okay. So electrons being negatively charged go to higher voltages. You might want to write that down somewhere. Electrons, comma, being electrically neutral or neutrally charged, either one you want to say, comma, go from high voltage, or excuse me, go from low voltage to high voltage. Go from low voltage to high voltage. So that's a key thing to get from this. Now that I've sort of got the basics down of electric potential versus electric potential energy, we can actually start to calculate things like what is the electric field of a parallel plate capacitor, or what is the voltage, say, in bringing a charge from infinitely far away into some distance r from a conducting sphere. So let's do some stuff like that, assuming no one has any questions. Anybody have any questions on this last example we worked? Guess not. Okay. Remember, these notes go up within 5 or 10 minutes after class. The video goes up, unless I have some internet problems, it usually goes up within a couple hours after class. So the video will be on my YouTube channel. I've named this, as if you could see, I don't think you can see it here. Yeah, you can't. What I've named this file is PHY242N01B. That's a 1, by the way. Underscore 090622. So if you go to my Google Docs and you want the actual notes, you go into Google Docs and just do a search for 090622, and it'll bring you everything that I posted today. Now, you just look for PHY242N01B and you'll be good to go. Not only that, most of my videos on my YouTube channel, if you happen to find one that looks like crap, because a lot of them do, that was back when I had bad cameras, I had bad lighting, I also had some difficulties with my internet connection, so often you couldn't read the notes at all, but you could hear my words. I took the time in most of those cases to actually take the notes, take photographs of them, and put them in my Google Docs. And I named it very much like this. I think I might have used PHY like 242 and maybe had an underscore between the 242 and the N01B or the D01B or whatever. But I still had the same sort of date scenario going. And in fact, if you look at the YouTube channel, inside the description of the video, it usually has something with PHY written in that box. That's the actual name of the file, only it cuts out underscores and leaves them in spaces. So you can always look for the notes for a given video that way. So make sure you use that as much as you want to. I've actually had a couple students asking for more examples, and they had wisely went to my YouTube channel, but didn't realize that they could get the notes from them. And that, of course, makes it, that's a whole game changer, because some of those old videos are crap if you don't have the notes. They're, you know, I ultimately will redo the same problems over and over again, and it'll have better quality. But until all those are replaced, it's just, that's what we got to do. So I apologize about that. Let's go ahead now and consider, for instance, what is the electric field if you have, say, a capacitor with a separation distance of, let's say, 3 centimeters, and it has a voltage of 3 volts. So let's say we have a capacitor, which is positive, 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 and negative, 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 negative. Let's say this distance is 3.0 centimeters. And let's say this voltage is 30 volts. And I'll put a dot after the 30 so we can pretend like both of them have 3 sig figs. So what is E? Well, that's easy enough. E equals a constant. We know that for a parallel plate capacitor. Therefore, we can use V is equal to ED. So we can say E is just equal to V over D. And V, of course, is 3.0 volts. And D is, of course, 3.0 times 10 to the negative 2 meters, which becomes 3.0 over 3.0 times 1 volt, or let's say 1 times 10 to the positive. Why did I write 12 there instead of 2? Good Lord. I did it again. What the heck? So this becomes 10 to the positive 2 up there, volts over 1 meter. So what I did was basically separate out the mantissa, which is the multiplier in front of the X on scientific notation. So you see these 3's cancel out to be 1, and I get, in fact, divided by, that actually is 10 to the negative 2. So that's going to be 100 volts, 100 point volts. Any questions on that? See if 3.0 times 10 to the negative 2, 3.0 times 10 to the, oh, I see. Hold on. Error there. Did everybody see that I changed the voltage to 3 instead of 30? That was a boo-boo. So let me fix that real quick. Okay. Well, heck, might as well erase that whole thing there since that went to crap. So here we go, everybody. I'm going to do it again. This time it's 30 volts over 3.0 times 10 to the negative 2 meters, which in this case is 3.0 over 3.0 times 10 to the 1 times 10 to the positive 2 volts over 1 meter. So that's me. That separating those fractions like that is just me trying to do the math without actually using a calculator. You can see that the 3's automatically cancel out when I make 30 into 3.0 times 10 to the 1. So that's why the 10 to the 1's on the right there. And then the 10 to the 2 came from the 10 to the negative 2 being in the bottom. So I end up getting 1,000 volts, which technically has to be, according to my sig figs, 1.00 times 10 to the third volts per meter. Lots off per meter there. So that also is something that I earlier mentioned to you, that the unit of the electric field is volts per meter. Any questions on that? All right, so let's look at another example. Let's say, let's determine the voltage for all R where the origin is at the center of a conducting sphere of charge Q and radius R0. So there's our problem. So imagine the coordinate system drawn like this, such that we have a sphere at the center, and we're bringing a charge in, say, from infinitely far away, and we're not even thinking about what happens with the charge. So we're not even using the charge for that. We're just literally trying to think about, hey, let's put the black end of my voltmeter in the ground, and let's sort of stick my red end of the voltmeter out in space infinitely far away, and then slowly move it. And as I move it closer and closer towards the origin of this coordinate system, I record all the voltage readings. Well, that's easy enough, because we know that as a sphere conductor, all the charge is basically going to be confined to the outer surface of the conductor, and it's going to be spherically symmetric. So it's going to behave just like a charged particle at the origin. Well, that's easy enough. What we know is that delta V, whoa, let's take it off of that thing. Delta V equals VB minus VA is equal to negative integral of E dot DL. Okay. So I'm going to imagine going off from, let's say, this distance R, and this will be out here at infinity. Okay. So E, the electric field, is actually going to be, if this is positively charged Q, then E is going to be equal to Q over 4 pi epsilon naught R squared. And it's going to point in that magical R hat direction, which again is me just telling you, hey, remember spherical coordinates? Well, there happens to be a vector that always points such that its tail, if you extended it however far you need, would run right to the origin, and its head would be at any point in space. That's what the R hat vector is. The DL, on the other hand, we can choose to use the DL to indicate what direction we're integrating, or we can choose to use the range of integration to indicate. This is again the difference between a line integral and just an integral. You don't have such considerations when you're just doing willy-nilly integrals. So what I'm going to do is I'm going to say the DL points in the direction that we're moving. Now we're bringing this particle in this way. So I'm going to say DL is equal to negative dr R hat. Okay, that means I take my range of integration to just be positive. So I'll write this here. So that indicates the integration direction. Now, delta V which is VB minus VA, is now going to be equal to the negative integral. So I'm going to go from small coordinate to large coordinate. And in fact, what I'm going to do is the small coordinate is going to be just plain R, and the large coordinate is going to be infinity. The way we deal with that, because you probably haven't had this yet, is you just put the answer down for what the integral is, and you take the limit of that integral as R approaches infinity, and that gives you the answer. So now I have Q over 4 pi epsilon naught R squared R hat dot negative D, negative GR R hat is equal to positive Q over 4 pi epsilon naught times the integral of dr over R squared R hat dot R hat. That's what I mean by the dot product being a linear operation. The R hat dot R hat, you can just pull the DRs and the K, Q, or any of that stuff right through the dot product. This part is just going to be 1. The integral of dr over R squared is negative 1 over R. So I get negative Q over 4 pi epsilon naught R from R to infinity, which ends up becoming negative Q over 4 pi epsilon naught limit as R approaches infinity of 1 over R minus 1 over R. So this part right here is clearly 0. So you end up getting that the electric potential for any distance R is K over 4 pi epsilon naught R. And that's only for R greater than R0. Okay. Now, if I want to have R less than R0, we know from Gauss's law that all the charges would be on the outside edge. And in fact, the electric field inside the static conductor is 0. So what we would do is we'd say delta V equals VB minus VA equals negative integral E dot DL from A to B. in this case, we're going from, let's say, just a plain r. We're going to say negative integral q over 4 pi epsilon naught r squared dr dotted with negative dr r hat. And that's going to go from r to r0. And then we're going to say minus the integral from r0 to r of 0 dotted with negative dr r hat. And actually, let me check my range of integration. Because I did a negative dr, I have to go in the increasing coordinate direction. So I went from r to r0. So actually, I did that backwards. Let me fix that real quick. So this integral right here, I have to change the range of integration because I indicated the direction I was integrating with my dr vector instead of with my range of integration. So this just has to be r0 to r. Okay. Now you can see this part right here is just going to be 0. But the other part becomes positive q over 4 pi epsilon naught integral dr over r squared. And this is from r0 to r. And in this case, you get the integral of r squared to the r to the negative 2 is negative 1 over r1. So it's q over negative q over 4 pi epsilon naught r. And that's evaluated from r0 to r, which ends up becoming, since r0 is in fact smaller than r, it's going to, when you put it in the bottom, it's going to be a bigger number. So if I wanted to, in fact, make this positive, I would want to have r0 be the first number. Well, let me just go ahead and explain what I'm doing. I'll say negative q over 4 pi epsilon naught times 1 over r minus 1 over r0. But r0 is less than r. So this would be like 1 over 2 minus 1 over r0 is actually smaller. Oh, excuse me. This would be like 1 over 12 versus 1 over 2. Okay. Obviously, 1/2 is bigger. So if I wanted a positive quantity, what I do is write q over 4 pi epsilon naught, and then write it as 1 over r0 minus 1 over r. Okay. So as long as r is equal to r0, you're just going to get 0. But what this tells us now is if we make a plot of the electric field as a function of r, and let this be r0, then basically the electric field up to here is q over 4 pi epsilon naught r0 squared. And out here it falls like 1 over r squared. But then it drops straight down to 0. And there. Now, if we make a plot of voltage versus r, again, we make this r0, then this quantity right here would be q over 4 pi epsilon naught r0. And this would go off like that. Okay, so this 1 over R0 minus 1 over R just gets us, say, from any particular R, like right here, from here to here. But once we get to there, then we're just adding this quantity right here, 0 to it, that we got for the second term. So it just has to stay Q over 4 pi epsilon naught R0, and that's what the voltage is. Notice again, we have a discontinuity equal to sigma, which would be Q over 4 pi R0 squared over epsilon 0. So that's again another discontinuity like we expect. Any questions on that one? Now, your book asks you a neat problem. I just sort of read this to you. It says when very high voltages are present, air can become ionized due to the high electric fields. Any free electrons in the air, which might be produced by cosmic rays coming from the sun or other places, hitting the atoms in our atmosphere and dislodging electrons. Any of those free electrons can be accelerated to sufficient kinetic energy to knock electrons out of the O2 and the N2 or any other things in the atmosphere as well. But O2 and an N2 make up the vast majority of our air. So that in fact makes a path of ions for electrons or for lightning to strike along, basically. And that lightning carries the electricity through the atmosphere. It's been found that breakdown voltage is about 3 times 10 to the 6 or 3 million volts per meter. What they're asking you to do is show that the breakdown voltage VBD for a spherical conductor is proportional to the radius. So what we know is that the voltage due to a spherical conductor is equal to Q over 4 pi epsilon naught R, and we know that the electric field needed for breakdown is equal to 3.0 times 10 to the 6 volts per meter, but that's also equal to Q over 4 pi epsilon naught R squared. So if I multiply R times E, I get R times Q over 4 pi epsilon naught R squared, which is just Q over 4 pi epsilon naught R, which is just V, which we call V breakdown. So V breakdown voltage is just equal to R, the radius of the sphere, which we can just call plain R, which is what I'm doing. Your book called it R0. Doesn't really matter too much, times the electric field at which the field is broken down. Now, what does that mean? That means for smaller radius, the breakdown voltage is smaller. So if you take a sphere and you make it smaller and smaller and smaller, it becomes more or less the tip of a lightning rod. So the very tip of a lightning rod sort of has a little arc over it, whatever. So that means the breakdown voltage is extremely low. So if you get a low voltage, but it's still high enough to break down for that low radius, then that will more or less sick the electrons or the path of the electrons to follow down that. And that's really how, in fact, how lightning rods work, is they chum the lightning by making a point where the breakdown voltage gets so small that it more or less has to. So over time, as the storms go over, it's just sucking charges down constantly because it's constantly breaking down. That's the origins of the term St. Elmo's fire, which of course they made a movie out of. Well, obviously they made a movie that was entirely had nothing to do with it, but at the end they said something about St. Elmo's fire. But basically, when you have a sharp object up in the near the mast, the top of the mast of the ship, running through a lightning storm or electrical storm, it's going to get a little glow around it because it's basically allowing little bits of lightning to strike it at all times. So that's some of the issue. Now, the final part that or I shouldn't say the final part, but one of the things that we have to work out now is what the electric charge is for a point charge. We've already found essentially what it was for spherical charge distribution. So we can now say that V for a point charge is actually equal to Q over 4 pi epsilon naught times R, where the point charge is in fact Q. So that's one expression. We already found that when we did the integration. We found that it's Q over R, because the other one, it was Q over R minus Q over R, the limit as R approaches infinity. And obviously that part was 0. So we got that. That's not a big deal. But what about charge distributions? And this is what we're going to work on next time. In that case, we say V is equal to the integral of dq over 4 pi epsilon naught R. Okay. So again, we have the idea that dq can be lambda dl, or it can be sigma dA, or it can be rho dV, and then these can be constant or functions of R theta phi x y dot dot dot. Okay, so I think that's a pretty natural extension of the electric field for a point charge to a continuous charge distribution. So we need not really go through too much through the derivation of that. But next time, since it's 6:36 and class is supposed to be over in 4 minutes, we will work on a ring of charge, just like we did before when we did Coulomb's law, both for force and for electric field. Then we'll work on using that result to find for a disk of charge, and we'll consider what happens when the disk is infinitely large, stuff like that. And from that, I'll also talk to you about, well, I'm not going to talk too much about equipotential lines and surfaces and how the electric field's found from it. But what I will talk to you about is mathematically, how do you get the electric field out of the voltage once you have the voltage, along a given axis or something like that. And we'll, of course, bring it back to dipoles. So that's about all we have left for chapter 17. I think that should give us plenty of opportunity to do chapter 17 by the 11th for part 1 of the homework, and by the 13th for part 2 of the homework. And of course, the concepts I think you can get right now, because we pretty much exhausted all that just from the hours of my talking. So I will wait for the last person to leave, but other than that, you guys are completely free to go. I'll stick around again, wait and see if anybody has any questions for me. AJ, you have any questions, sir? All right, he might not be here anymore, so I guess I'm going to let it go. Have a good one.